on leave being a principal research scientist at Amazon Research. And she's going to actually move to Caltech, back to academia next year. Looking forward to her talk on distributed optimization on AWS.
Thank you. I'd like to thank Martin and all the organizers, for inviting me here. Everybody's been very hospitable, and it's a very nice event. So today I'll be talking about my new adventure. I've been at Amazon for the last few months, and if you've come to my other talks, they've been more in the area of spectral methods, and this talk may seem a switch from that, but in the end I'll try to kind of connect and say what roadmap we have to bring different concepts together. So today I'll be talking about how to carry out distributed deep learning at scale, running this at scale on the AWS cloud infrastructure. So there's been a lot of research done in deep learning. It's shown tremendous improvements in performance. But I think one aspect that has received less attention has been on efficiency, right? So there has been many interesting works in the area of distributed optimization, including some of the talks we heard here, like Martin's talk. But how can we deploy this with deep learning, and how do we exploit the cloud infrastructure that's present at Amazon? So these will be the aspects that I'll be covering today. So what's fueling this excitement and growth in artificial intelligence and machine learning is, I would say, three aspects, right? So first, we have these exciting algorithms, an array of algorithms for large-scale learning. And what fueled this was the availability of large-scale data sets. Like if we didn't have data sets, if we didn't have ImageNet, right, probably many of these innovations would not have occurred. And the third crucial component is, of course, computing. The concept of neural networks have been around for a long time, as we saw in the talk yesterday, right? But what's made this dream possible is the availability of large-scale infrastructure. And Amazon, has developed a whole host of services to enable computation at scale. And so I would argue that a lot of these, methods can run very well on this infrastructure. And there is also room for very exciting research at the intersection of systems and machine learning. So as we've seen in several talks here and elsewhere, deep learning has revolutionized performance in a number of domains, starting with image analysis to speech recognition, natural language processing, right, and down the line into reinforcement learning and self-driving cars. So we have this whole framework, whole range of domains where deep learning has shown enormous improvement in performance. And arguably, a lot of that improvement has come from the fact that deep learning is highly flexible. So, unlike probabilistic models where you make a lot of assumptions on the underlying data structures, here it's much more flexible. And once we have lots of data as well as compute power, we're able to push the boundaries of accuracy in several domains. Right? But when it comes to deploying deep learning in the real world, there are a number of challenges. So the network that I've shown there is the residual network, or ResNet for short, and that's the state-of-art network, right? So that has the best performance on ImageNet as of today. And as you can see from that network, it's a complex array of connections, right? So if you think about trying to program this from scratch, this would not be possible, right? So we need good paradigms of programming as well to incorporate such complex network architectures into our machine learning framework. So when we think about a framework for deep learning, one of the important aspects is programmability. So can we have simplified programming interfaces that can implement such complex network architectures, right? And there should also be easy to debug as well as, say, modify the network. Suppose you want to modify maybe a few connections, you shouldn't have to code from scratch, or you shouldn't have to recompile, and you should be able to debug efficiently. So this will be one of the important aspects we'll be focusing today on, how to have such a paradigm. The other one is you also want portability. So now deep learning is being run on an array of different compute platforms, right? All the way from large-scale cloud infrastructure to local clusters, maybe your laptop, maybe your cell phone, a smartphone, right? So a whole array of different devices where you want the same algorithm or similar algorithms to be run. So in this setting, how do we enable the portability of code across different platforms? So this will be another important consideration. And of course, depending on where you're running the code, other aspects such as memory usage becomes very important. If you want to run this on your phone, then there is limited amount of memory. So having a highly optimized framework for memory utilization is very important, right? And the last aspect is, of course, efficiency. So, as you increase your compute power, as you, add in more GPUs, or as you add in, more even CPU power, right? How do you get the best performance out of that? So ideally, you want your efficiency to be 100%. So meaning now, if you have 2 GPUs in place of 1, the amount of efficiency you get should also be doubled, right? So that linear scaling is the ideal one. How close can we get to the ideal one, right? So of course, in practice, it will not be 100% because there'll be overheads. Once you start having multiple devices, you have to worry about how do they communicate with each other, right? How do they synchronize with one another, right? So there is a lot of overhead that will be built in once you have multiple, either GPUs or multiple machines. So, and you also need fault tolerance, for instance, if there is failure. So how do you incorporate all these aspects of large-scale systems, but at the same time ensure that you have good efficiency for these deep learning algorithms? And why I also want to emphasize efficiency here is what we are pushing for is to enable deep learning on the AWS infrastructure, right? We want to make this accessible to everyone on the planet. That's our ultimate goal, to level the field when it comes to being able to run deep learning at scale. And if we are to do that, then cost is an important consideration. If people are paying for the cloud time, they would like the most efficient deep learning library that can bring down the costs. And so this is now a rich ground for further research on how we can scale up algorithms and at the same time maintain efficiency. And I would argue that this aspect has received much less attention from the machine learning community until now, and I expect there'll be a lot more of it in the coming future. And our group is leading some of those efforts in that direction. Yeah, so there are a number of different deep learning frameworks, and so you saw talk about TensorFlow. There is, of course, the Caffe. There is, CNTK. There are a whole range of different frameworks. And today, what I'll be focusing on is MXNet, and I'll be showing you some of the advantages that it has and some of the flexibility that it has, as well as the efficiency in a number of different scenarios. So I'll also at the same time show you towards the end of the talk that AWS supports all these frameworks, right? So suppose you want to run any one of these, you can easily run them on the cloud infrastructure with just a few clicks. I'll show a short demo on how to do that. But what I'll focus today is how MXNet is very competitive in a number of aspects. such as programmability, right? It's very easy to program in this MXNet framework. It's portable. You can run it across different platforms very easily, and efficiency. I'll show you some benchmarks on how we can get very high efficiency, not only across multiple GPUs, also across multiple instances of that. And I believe these will be some compelling reasons to employ MXNet, if you're doing deep learning. And so officially, MXNet is, the recommended platform of choice for AWS. But of course, we don't limit you only towards doing that. If you're interested in having some other framework, you can also use it with the AWS infrastructure. And other two compelling reasons to use MXNet, most recently, it got accepted into the Apache incubator. So which means it's truly open source. So all the work will be, putting into MXNet will be open source. So you can also run it on your local cluster, on your local machines, in addition to running it on the AWS, right? So it's not limited to the AWS infrastructure. You can run it anywhere you want. And the efforts that we are doing in our group is to do research on new algorithms, as well as contribute to the code base and grow this open source community. And in fact, the history of MXNet started with university efforts, and this is certainly something we want to encourage and continue with. And the other aspect, as I said, of course, is this is the most highly optimized set of tools when it comes to efficiency on AWS infrastructure and good integration with the AWS infrastructure. This is the best one. So let me now cover give you some more details on the claims I made, right? So the first claim I made was about programmability. If we have complex network architectures and complicated math equations, such as various gradient descent and other equations you want to implement, you want a language that makes it easy to write. It should be small number of lines of code, and at the same time easy to debug, but you don't lose out on efficiency, right? So usually languages where it's easy to write will mean that you don't get good efficiency. So can we get best of both the worlds, right? So here I've shown multiple languages. So I want to have a survey and see how, what people are most comfortable with. So how many of you are most comfortable with C++? Given any other choice, you would only use C++ and not the others. No one? Very few, right? So unless you are an expert programmer, C++ is probably not your first choice. What about Python? Yeah. So that's expected, right? But if you just run Python language as it is, it's not going to get you good efficiency. It's going to be very poor, right? What about Scala? Yeah? Yeah, quite a few. R? Yeah? The statistics community uses R, so that's another community that we shouldn't be forgetting. Julia? Good. OK, so there are two. MATLAB. Yeah. So there's JavaScript and Go. So there's, I think there is. So as you can see, there is a whole host of languages. And depending on your background, you may have one language that's your preferred mode of programming, right? Whereas now with every new package, what happens sometimes is you have to learn a new framework. So instead, what MXNet, the philosophy that it takes is you can have any of this as the front-end language, but there is an optimization that occurs under the hood where, that's through a C++ intermediate layer where you can now run it both on GPU and CPU, right? So there is a common front-end code that's say maybe in Python or R, which is simple to read, it's simple to write, but then you get the efficiency of highly optimized backend operators. And also we are now making it easy to define these operators, right? So far, like there has been built-in operators that let you, for instance, call for a forward pass, call for a backward pass, different operations that arise in deep learning. So one avenue that we are pursuing now is to really expand that whole array of operators. So once you have operators, right, for different functionalities, then you have to worry less about how it's done in the back end, right? Unless you're an expert, maybe you don't want to worry about what happens in the back end, but you write your front end in your favorite language, right? So you can then easily modify and customize the code for your needs, right? Suppose you want to slightly change the network connections. Suppose you want to, add in, say, new layers. This will be much easier to do now without having to worry about what happens on CUDA, what happens in MKL libraries if it's CPU. And so that's one of the advantages here, that this has the most, the widest range of front-end languages for you to be able to program in. Yeah, and so to contrast, not only that, so not only having this availability of different front-end languages, the other aspect is what is the philosophy of programming, right? So one philosophy is this imperative programs. So this simple Python code here, if you write it in Python, the idea is this is imperative language, right? So meaning you just interpret the program lines one by one, right? So the compiler just goes one by one and interprets what the operation is. And of course, it's extremely simple to write, and it's easy to read the program. I mean, you already know what the program is doing here. And on the other hand, this is really bad for optimization, right? Especially if you're writing parallel programs, this is terrible. Python is quite a bad language to, if you want to directly use that for parallelization. And so that's the pros and cons, that this imperative programming is how our brain thinks, right? We think in a sequential manner. It's easy to write the code, it's easy to debug, but it's bad for optimization. The other framework is the declarative programs, right? So here what you do is you first declare what the variables are, what the operations are, and so this way you can first have a compute graph. So the idea here is first A and B are being added up, and then you're adding up to that intermediate result another number, right? So if you have this computation graph, now you can do memory optimizations. Because now you know that this intermediate operation that requires here, right, you can overwrite that. Like you don't need it once it's computed and passed forward. And so you need now much less memory than in the imperative setting. Right? In the imperative setting, you don't know beforehand what the oncoming operations are, so you cannot allocate memory beforehand. But now with a declarative program, because you know the overall computation graph before you start any operation, right, you can do all the optimizations beforehand, before you run any training procedure. And so now this lets you do memory optimizations. But of course, the difficulty is usually, sorry, that was not the right overlay. The difficulty is usually these tend to be much longer programs. So if you're an expert programmer, you're used to this declarative style of writing, this is okay, right? But it's very hard to then read somebody else's program or to debug it because, the length of the program just grows very fast as you have complex, operations. And so instead of saying one versus the other, the framework that MXNet does is it gives you the ability to mix the both, right? So you can choose what framework of programming you want to use. You can write it in the imperative style, or you can write it in the declarative style, right? So it lets you do both, whereas other frameworks, such as, say, TensorFlow, only is imperative, right? Whereas, if it's MATLAB, TensorFlow is declarative, and if it's, other frameworks are only imperative. So here you have the flexibility to mix the two, and if there are, say, settings where it makes sense to write the imperative framework, you can mix that with the declarative one. To just give you a simple example here, the first few lines of it are for, like it's declaring the network, right? So it's declaring a network, it's loading that, and then it's doing a forward and a backward pass on the batch. And so that's declarative programming, right? Of course, I haven't shown the details of what those do, but then you can, have declarative programming for those parts that define the architecture. And if you want to do now the gradient step, you can write it in your imperative style, because that's most convenient to, if you're writing math equations, typically the imperative style of programming tends to be a lot easier to write. Right? And that's why MATLAB is highly used if you're using it for mathematical programming. So so those that involve say things like gradient updates, you can write it in imperative style. And for defining the network architecture, where again it's crucial to do the memory optimizations, you can write it in declarative style. So now you have the flexibility to mix the two frameworks. Right? And so that's the idea. You can embed symbolic expressions into imperative programming and vice versa. So that was about programmability. So what MXNet offers is a whole array of different front-end languages. So depending on your background, depending on your preference, you can use any one of them to have your front-end code. And all the optimization occurs in the back end through a C++ interface layer. And you can do this interface through the notion of operators. So you can define some functionalities that will be useful across different programs, and you need to write that only once, and then use it across the course of development for your deep learning frameworks. And the other aspect was the ability to mix declarative and imperative programming. And now this lets you a lot more freedom on how you want to write your code. So the next aspect I'll briefly cover is portability. Right? So as I mentioned, you would like the ability to run the same piece of code across multiple platforms and devices. So one thing that MXNet lets you do is deploy on any platform, because the idea is everything is compiled into a single C++ source file. Right? So all the dependencies, everything is inbuilt, and so you don't have to worry about it. So everything is now into one C++ source file, and now you can compile it across different devices. And so this makes it very convenient to move it across platforms. And here, this short demonstration is doing image recognition on the smartphone, and this is done using JavaScript. So you can run this in the browser, and you can start doing image recognition on any image you load onto the browser. And so it makes it very easy to port the code across different devices if you use MXNet. Right, so and now performance, right? So as I've been saying until now, performance will be one of the crucial aspects if we have to scale up machine learning, and if we have to do it on very large, large-scale infrastructure. And so in deep learning, you have both performance for inference and performance for training, right? So depending on both are important. So typically inference is important if you've already trained and you're just now hosting this, whereas training would also be important if you're continuously developing, having new data, and you want to update your model. So both are important. Performance is important for both these settings. Right. So as I said before, there'll be a number of factors that will inhibit our ability to scale up across different scales. So one would be first looking at multiple cores, right? So even if you take a single GPU, it's made up of thousands of cores. Right, so you need to write programs with a view of making sure that you make it as embarrassingly parallel as possible. And so that's where if you use, say, cuDNN or cuBLAS, I mean, these frameworks are already optimized to run on GPU cores. So a lot of parallelism is taken care of if you use those libraries. So in a way, scaling across multiple cores on a single GPU is not that hard because that's where NVIDIA and say Intel for MKL, right? So they are innovating on that front. So, but what's I think harder is if you want to now scale across GPUs and across machines, right? I'll show you how, like Amazon has this P216 extra large instances, and that's the largest GPU instance you can request on Amazon. And so now you've requested multiple GPUs. How do you ensure that you scale up well on them, right? So in this case, in a single instance, you can request up to 16 GPUs. So how do you scale up? That would be more important. And of course, down the line, you may request multiple such instances, right? So not just one AWS instance, but you have multiple instances and you want to scale across them. So this is scaling across nodes, and this is going to be even harder, right? Because there'll be more overhead in communicating across the nodes. But these are the arenas that we want to optimize for and ensure that we get the best possible performance. Right, I mean, if you think about parallelizing programs, right? So you've written a single machine program, you want to parallelize it. It's extremely painful. If you try to do it from scratch, like how it was being done in the old days with MPI or other frameworks, it's extremely hard. So I don't think you can read all of that, but the point I want to make with this figure is how even just thinking about one forward and backward pass updates can be very complicated to write if you have these multiple GPUs, right? So the idea is which part of the computation should go to which GPU and when should it be communicated back to the CPU and when should it go to another GPU, right? So this is can be very tricky if you try to write it from scratch. So that's not what we want to do, right? So we shouldn't be writing this from scratch. And so the framework that MXNet employs is this notion of a parameter server and a hierarchical parameter server, which is multiple levels. So the idea is at the lowest level of the hierarchy are these workers, right? So in deep learning case, that would be GPUs because GPUs give us the best performance. So you have these multiple GPUs at the lowest level, and those are the workers. And then you have a server that takes in the updates from the GPUs, combines it, right? Typically, it averages it and sends it back to the individual workers. So in this framework, for MXNet, we'll declare one of the GPUs as the level 1 server, right? So we wouldn't be sending it back to the CPU in each run, right? Because that would be terrible. The bandwidth to do that is much more limited than when it comes to GPU-GPU communication. So if you see here, GPU-GPU communication is several times faster than GPU to CPU, right? So you want to, as much as possible, just have peer-to-peer communication between GPUs and only communicate with the CPU when necessary. And of course, the next level, like accessing from the disk is going to be even slower, or accessing across the network will be slower, and you want to avoid that whenever possible. And so now you have these optimization that's done at multiple levels on how you want to maintain communication as much as possible within these GPUs and only communicate with the CPU when needed. And what MXNet offers is a simple way to specify, which one is going to be the server, which one is going to be the workers, and how to, send the updates. You can do both synchronous and asynchronous updates on MXNet. So there's a lot of sample code. I didn't put this up here, but it makes it very easy to now, specify the protocol for parameter server and lets you, do a lot of computations within the GPU framework. Right, so I'll show you some benchmarks. All these benchmark code is also, by the way, available on GitHub, and you can spin up your own cluster and either verify them or add new benchmarks if you go about, trying out some of these frameworks. So the first one is with, 16 GPUs. So if you take one P2 instance, right, the large instance, it'll give you 16 GPUs in one shot. And so what the ideal one should be linear scaling, right? So with each new GPU, you should get an additional linear scale up. And so now you can see that we are very, very close to this ideal one. So we have an efficiency of 91%, which is very good. And this is across different networks. There is the Inception, the ResNet, the AlexNet is the older one. So the modern networks, you can see, get very high efficiency on this framework. And now you can also request multiple instances, right? So now this is 256 GPUs, meaning it's 16 instances where each instance is 16 GPUs. And again, you get, you do suffer a bit because as expected, as I said, if you're scaling across nodes, right, there's going to be more overhead. But we've done our best to limit that overhead. And you can see that you still get 88% efficiency in this framework. And just some details on how we did that. I won't talk more about it. But again, if you go to those benchmark there, we've documented all this in detail. So in the next few minutes that I have left, I would like to now demonstrate how we can do this seamlessly on the AWS infrastructure, right? So, the idea is traditionally if you had to set up deep learning on AWS or other cloud infrastructures, you had to download all the libraries, set up a cluster, right? It would in fact, there were companies doing that for you because it was quite a hard thing to do. It took time. But now what we've made it easy is we've automated everything. So we have these what's called Army or Amazon machine images where everything is preloaded, and with a click of a few buttons, you can get your deep learning going, right? So, many, I think advantageous if you run this on AWS is, as I said, we have the largest collection of GPU instances available, and these P2 instances are very powerful. And the other aspect is we have pre-configured deep learning frameworks that lets you do this. And it also gives you the ability to define your own deep learning clusters by combining multiple such armies. And to just give you an idea of the amount of compute power you can, request on AWS is if it's a single, instance of P2 16x large, right? That's about 70 teraflops. And if the experiment that I showed you had 16 of such instances, and that's about 1 petaflop, right? And if you think about the world's fastest supercomputer, that's 93 petaflops. So you can, of course, the cost of building that supercomputer was enormous, and it's not accessible to the public. But now with the AWS infrastructure, it levels the ground. Anybody can go and request this amount of compute power. And I think this will drive a lot of innovation in enabling better and more interesting uses of machine learning. And of course, all these come with these very fast GPU to GPU communication that lets you have a lot of efficiency when it comes to learning these deep learning packages. All right, so just to briefly give you the link for the ARMY, again, if you Google deep learning ARMY, that should show up. So as I've noted here, everything is preloaded. So it's not just MXNet. You have these variety of other packages that's available on the ARMY as well. And you have all the drivers, both the GPU and CPU drivers, everything preloaded. So it makes it very easy to do that. So let me very quickly show you how to, so again, you wouldn't be able to follow all the details because it's one of my lab mates who did this, who's very fast, so you wouldn't be able to follow every aspect of it. But the idea is you can start this CloudFormation console very quickly on AWS. You can create the stack. So what's happening is you're creating the stack using some predefined template. And you can load it onto S3, that's the storage. Now you're requesting what is the type of the instance. Right, you want a large instance, you load your keys, the SSH location, how many workers you want, right? And you can, of course, name your stack. This was done for NIPS, as you can see, so I'm reusing that. So with just a few clicks, now, you can already set up what you want to do. And, so that's it. You acknowledge, and you've started your CloudFormation template. Right, so that's all it took to start deep learning, and now you can track it. You can keep tracking the progress in terms of what your stack is doing, right? So now it's created, right? So there is and you can go to the EC2 dashboard and to have cloud metrics, see what the what the status is, what things are happening. So now the workers are available, and you can start running your code, right? So now you can start training your model, and for that, of course, you have to SSH to your code base to launch the job, and this is the open source code base that we have. So that's it. We've launched it, and now we are gonna it's gonna start training now. So you can see that it was very quick to set up all this and to start doing deep learning with a few clicks. And you have the ability to, of course, verify that it's running well, and you can continue with that. So I just wanted to give you that flavor and show how easy it is to do deep learning on AWS infrastructure now. And we have several exciting things that's going to be coming in future. That's what the effort of the lab is, to think about innovations in machine learning as broadly, and at the same time contribute to open source code base and have highly efficient algorithms running at scale. So in the short term, some aspects such as documentation, I would say we are actively working towards improving it, because it started as a university effort. It doesn't have the same level of documentation that some of the other ones do, but this is where we also need more volunteers and more partnerships with universities to grow this open source effort. And several other aspects of how to add new functionalities into MXNet. For those who've heard about my research before, I worked on tensor methods. So one thing we're actively doing is incorporating a lot more tensor functionality into MXNet. And another aspect is also sparse functionality. The traditional deep learning does not require sparse data types, but that's not true if you use it for other frameworks such as recommender systems. And those are immediately on the roadmap. You'll be shortly seeing them added in as well. So there is, now a whole ecosystem that we want to build in the open source community that will enable us to not only have deep learning, but have machine learning of various flavors that's integrated well, that has good software support, and that can run efficiently at scale. And anybody is able to access that infrastructure and build their own algorithms. Of course, let me first talk about this. Of course, when I say anybody can access, you may say that it's not a level playing field, right? It's and that's where we are making a lot of efforts to provide more AWS credits to universities and nonprofits, and also actually startups. That's a different program, but yeah, to across different entities, we want to provide AWS credits. And this particular one is for research, the link I sent. There's also another one for education. There's another one for startups. So we want to enable people to be able to run on AWS and innovate further, and we want to encourage that. And of course, at the same time, we are hiring very actively, both internships and full-time positions. So you can send me an email if that's interesting to you. So just to end, we have a number of other exciting efforts at AWS in the AI space. What I talked about today is the MXNet, which is the deep learning package. We have launched a number of other services, including Poly, which is text-to-speech, that enables you to have like a more realistic speech and encode that into the framework. There's the recognition, which allows you to do a variety of image analysis, right? And there is Lex that does automatic speech recognition and natural language understanding, and makes it seamless for you to start deploying it into your applications. And more of this is available on the website. I didn't have a chance to talk about it, but I'll be happy to talk offline as well. Thank you.
Questions, comments?
Just one strange thing I noticed is that you said that Torch is imperative programming system, but you can actually define the declarative style, like your layers and your network. So it's very similar to what MXNet is doing?
So I have to check on that. So I think, yeah, so I have to check on that. I'm not sure, yeah.
Well, if not, let's thank Anima a lot for coming and giving a wonderful presentation.
Thank you.